GCSE Physics boosters, velocity time graphs. Okay, always look at the labels on your graph. This isn't distance time, this is velocity time. Don't get them muddled up. Now, in this video, we're only going to consider motion in a straight line. Velocity is a vector, it has direction. Don't worry about that in this video. In this video, you can think of speed and velocity as being the same thing in this video. So if an object is traveling at a constant velocity, then its velocity isn't changing. For example, a car on a motorway going at 70 miles an hour. So it's just going to be a horizontal line. That's the velocity time graph if it's going at a constant velocity. Now, this object is accelerating. Yeah, it's speeding up. It's speeding up from rest. You see that the line goes through the origin. And it's a uniform acceleration, and that means its acceleration doesn't change. So every second, its velocity gets bigger by the same amount. Okay, every second its velocity gets bigger by 3 meters per second. So it's 3 meters per second. That's uniform acceleration. Now, if the acceleration is uniform, then the velocity time graph will be a straight line. And the acceleration, we said, is the change in velocity divided by time. So that is going to be the gradient of the line. Okay, so looking at the two graphs here, if you get the gradient, the change in velocity divided by time, whether it starts at the origin or not, or whether it has an initial velocity, okay, it's delta V over t, change in velocity over time. So meters per second. It's how much the velocity changes every second. So meters per second, which is meters per second squared. Have a go at this sum. A car accelerates uniformly from rest, reaching a velocity of 20 meters per second in 4 seconds. Calculate its acceleration. Dead easy. And the answer is, there you go. So change in velocity over time, 20 over 4, 5 meters per second squared. Look at this train. Have a go at this question yourself. A train traveling at 30 meters per second slows down to 10 meters per second in 20 seconds. Calculate its deceleration. Pen, paper, calculator, do it. And the answer is in 3, 2, 1. There you go. So A equals delta V over t. For the change in velocity, now the change in velocity is actually negative because it's gone from 30 to 10. But as I've called it deceleration, then I don't need to really worry about the negative. I know it's slowing down. So 30 minus 10 divided by 20 is 1 meter per second squared. We could say it has an acceleration of minus 1 meter per second squared. Here's something for you to have a go at. This is a journey. It might be somebody goes for a ride on his bike, something like that. Well, he's pretty fast on his bike anyway, but describe the journey of this vehicle, calculate the acceleration at each of the 3 stages. Now remember, you're describing what's going on in the graph. Give plenty of detail. We want numbers. So I'll show you my answer in 3, 2, 1. Okay, between 0 and 30 seconds, it accelerates uniformly from 0 to 25 meters per second. That's the level of detail you need to say. Between 30 and 60, it travels at a constant velocity of 25 meters per second. And then between 60 and 120, it decelerates uniformly to rest, from 25 to rest, to 0. Plenty of detail. Give numbers in your answers. The accelerations, look at the sums below. Okay, change in velocity over time. Where the graph is horizontal, its acceleration is 0. And for the last bit, I've given the acceleration as being negative because it's slowing down. So the change in velocity is negative, so its acceleration is negative. So minus 0.42 meters per second squared. You could just say it has a deceleration of 0.42 meters per second squared. So now an object travels at 20 meters per second for 20 seconds. How far will it have traveled? Well, 20 meters every second, and there's 20 of them, so the answer is going to be 400, isn't it? Okay, now 400, look at the graph, it's a rectangle, 20 times 20. Okay, that is the area of that rectangle. The distance traveled is equal to the area under the graph. In this case, it's a rectangle. Okay, doesn't have to be a rectangle though, and the area under the graph is equal to the distance traveled. On the first diagram, it's going to be a triangle, so half base times height, and on the other two diagrams, it will be a trapezium. If you had to work out that area, you should know the formula for a trapezium, the area, or you could just say it's a triangle plus a rectangle. It's up to you. Okay, but the area under a velocity time graph is equal to the distance traveled. To get the distance traveled, or to get the area, what you might have to do is count squares. It does say on the specification that you might have to count squares. So every square on this graph is 2 meters, okay, because it's 2 meters per second for 1 second, so that's 2 meters. So estimate the distance traveled by this object in 10 seconds. Have a go. And you should get, in 3, 2, 1, well, you should get about 100 meters, because it's our friend Usain Bolt again.